In this experiment, we will study about the CE amplifier. The aim of this experiment is to construct a CE amplifier and to study its frequency response curve. We'll also be finding out the input impedance, the output impedance, and also the bandwidth of this CE amplifier. This is the circuit of the CE amplifier. This is a typical voltage divider bias circuit. We have a transistor and we have two resistors on one on collector side RC and one on emitter side RE. To bias the base of the transistor, we have two resistors R1 and R2, and we give the input to the amplifier with a signal generator which generates a sinusoidal waveform, and we feed it to the amplifier through a capacitor. A capacitor filters out all unnecessary DC components and lets only AC component of the generated signal to pass through the amplifier. And when we are taking the output, we also use a capacitor here. That also only lets AC component of the output to come out, and DC component is blocked. We take the output across the resistor RL, and V0 will be our output. We also have another capacitor here, CE, which will ground all AC components, but we have a resistor RE which will not ground the AC components of the signal. We make the circuit connections as shown in the circuit diagram, and we give input to the amplifier through the signal generator. The signal generator generates a sinusoidal waveform, and the peak-to-peak value of this waveform we set it to 20 millivolts. We call it as VI or Vin, and we set it to 50 millivolts. Then we set the frequency of the input waveform to 50 Hz initially, and then we keep increasing the frequency in terms of the semi-log graph sheet until we reach 1 MHz. We take the corresponding output values measured across RL for every value of input frequency, and we tabulate it in the tabular column. And for every value of output voltage obtained, we also obtain the gain, the voltage gain of the amplifier, which is given by the formula Vout by Vin or Vo by Vi. After we calculate the gain for every value, we also need to calculate the gain in decibels, or otherwise called as power gain. We calculate that by given formula 20 into log to the base 10 of voltage gain, AV. After we calculate that, we plot the values of voltage gain versus frequency on a semi-log graph sheet. If we plot all points of frequency on the semi-log graph sheet, we obtain a graph like this. You can notice that the gain increases initially and then remains constant at a maximum value and then decreases at higher frequency. Frequency as increases, we get an increase in gain, then a constant value of gain, and then a decrease in gain. This part is called as the lower frequency part, and this part is called the higher frequency part, and this part, the constant gain part, is called the mid-range frequency part. We need to calculate the bandwidth of the amplifier. So how we calculate bandwidth is, we take the maximum gain value and call it A max, and we obtain a value of gain which is A max by U2. For this value, which will be slightly lesser than A max, we plot it on the graph. And we draw a horizontal line parallel to the x-axis to make a line which meets the frequency response curve at 2 points. The first point, it intersects the frequency response curve, we call it as f1. And the second point, we call it as f2. So we have two frequency values, f2 and f1, and we know that f2 is greater than f1. So what basically bandwidth is it's a range of frequency at which we get a good amount of gain from the amplifier. So we can calculate the bandwidth by subtracting f2 with f1. So bandwidth give us the bandwidth of the amp. This is the circuit we need to construct. And to construct the circuit, we need to know our resistor values and the capacitor values. We have certain values which is given to us before performing the experiment. We have VCC equals 12 volts. We have the frequency equals 100 hertz. And the coupling capacitors CI and CO is equal 0.1 microfarad. The collector current IC equals 4.7 milliamperes. And the resistance R2 is assumed to be 4.7 ohms. The beta value of the transistor is equal to 100. We know that for all transistors, IB, the base current, is very small, so we can assume IC equals IE. And we also have the relation VE equals VCC by 10. By substituting the values, we can get the value to be 1.2 volts. VE is the voltage across the resistor RE. Then from this equation, VE equals IERE, because it's this resistor, we can calculate the value of resistance RE from this equation, which will be equal to 266.66 ohms. Now we apply KVL to the output section of the amplifier, which is basically this part. So we get the equation VCC equals ICRC plus VCE plus IERE. We know that VCE equals VCC by 2. So we have VCE equals 6 volts. We substitute this value back into this equation. So we get 12 equals ICRC plus 6 plus 1.2, because IERE equals VE, which is equal to 1.2 volts. So we substitute it here and we obtain the value of RE because we know the value of IC. So RC will be 1.06 kilo ohms. We next need to calculate the VTH value. VTH is basically voltage at the input, VB, which is basically the voltage between the base and the ground. We have this equation, VTH equals VB equals VBE plus VE. VBE plus VE. So we have another equation, VTH equals R2 into VCC divided by R1 plus R2. We have this equation from the voltage divider rule. So we substitute the values here and we get this equation. And we also substitute for VTH from this, which is VBE plus VE. We know that for all transistors, VBE equals 0.7 volts and VE, we know the value from before as 1.9 volts. So by substituting this into this equation, we finally get this equation. From this, we know that R1 is the only variable here. So we solve for R1 and we finally get R1 equals 24.98 kilo ohms. Here we have XCE, which is the impedance across the capacitor. We know that this is equal to RE by 10. This impedance is also given by another equation, XCE equals 1 by 2 pi F into CE. F is the frequency of the amplifier. Now we can solve for CE because we know all the other values. By substituting this into this equation, we get CE equals 1 by 2 pi F into RE by 10. By solving for CE, we get CE value as 61.21 microfarad. Now, thus we have all these values that we have found out. We have R1 equals 25 kilo ohms, R2 equals 4.7 kilo ohms, RC equals 1.06 kilo ohms, RE equals 266.66 ohms. CE equals 61.1 microfarad. Yeah, this is a transistor and the emitter. Starting from that, we can count as emitter, the center one is base and the last one is collector. Now we place this on the breadboard. This is emitter, base and collector. Now we have, if we assume this and this as ground and VCC, we have RC, which is the collector resistance, from collector to VCC. And then we have RE, which is 220 ohms, from emitter to ground. And then we have an electrolytic capacitor at the emitter to ground. Now we add the other two resistors R1 and R2. R1 is from collector to base and R2 is from base to emitter, which is grounded. Now we connect R2. This is our input section, and our output will be taken across RE and ground at the point. We connect the coupling capacitors to the input and the output. And then we connect wires for VCC, ground, and input and output. So VCC, this is for ground, this is for the input, and this is for the output. Now that the circuit connections are made, we connect it to the CRO and signal generator to get the output. We need to set the VPP at 0.2 volts, and then we connect the input and the output. The output of the signal generator is connected directly to the CRO by directly connected crocodile pins. We set it to 50 millivolts in the dial, and then we make that coincide with one box so that we have 50 millivolts of peak to peak voltage. Now we then connect this to the output of the CE amplifier, the CRO probes to the output of the CE amplifier, and the signal generator probes to the input. The input is the one which is connected to the base. And then we set the dial voltage to 1 volt, and then start taking the reading. We start taking the reading by setting the signal generator value to 50 Hz first. We can see that the output is occupying one of the small blocks, so it's 0.2. Then we keep increasing the frequency in the signal generator. We set it to 100. Now it's almost occupying one box, so its peak to peak value is still 0.2 volts. We keep increasing in steps of 100 Hz for now. We set it to 200. Now it's occupying two blocks, so it's 0.4. We set it to 300. Like this, we keep increasing the voltage of the signal generator. We take it at 300, then we set it to 500, then we set it to 1K, 2K, 3K. Now we'll set it to 1K. And we can see that it is occupying almost one box and 4 of the milli divisions, small divisions. So the voltage value is 1.8 volts. Now we can see that the voltage is actually increasing from the initial value to the current value. As we increase the voltage in the beginning part of the frequency, we see an increase in the output voltage.